Hello everybody, I am Sushil Verma from Georgia Tech, and today I am going to present my joint work on dynamic pricing and matching for two-sided queues with Pompavi Bumpensanti, who is another student at Georgia Tech, Professor He Wong, and Professor Sivateja Maguluri. Let's look at the overview of the talk. We'll first talk about what a two-sided queue is, then we'll look at its applications, which will highlight why it is important to study a two-sided queue. Then we'll look at the stability, which I will point out to be non-trivial. We'll then look at the model and results in the paper. In a two-sided queue, the customers and servers both arrive in the system, unlike a single server queue where the server is fixed. The service in two-sided queue is defined as pairing up a customer and a server. So as soon as you pair up a customer and a server with each other, they match with each other and they depart from the system instantaneously. The service discipline we consider in this paper is first come first serve. Now, let's look at the applications of two-sided queue. Some of the more intuitive application includes dynamic barter exchange and ride-hailing system, whereas there are also a lot of non-trivial examples, which includes routing cryptocurrency in payment processing network and quantum entanglement switch. I will not go into the details of these systems, but I would just like to point out that two-sided queuing model appears in a lot of different systems naturally, and that's why it's important to study it. Let's consider ride-hailing system in more detail. You can divide the city into different geographical locations, and each geographical location determine a type of a customer or a driver. Depending on their location and geographical proximity, there will be a compatibility graph between the drivers and the customers. In short, we have a bipartite graph with different nodes determining the geographical locations of different cars and customers, and a compatibility graph between them, which determines if we are able to match that type of customer and the server. Let's look at the differences between classical queue and two-sided queue. In classical queue, the servers are fixed, whereas in two-sided queue, they arrive in the system. In classical queue, the service discipline is a finite time. So there's a fixed server, the customer arrives, and then the server takes a finite time to process the request of the customer. Whereas in two-sided queue, the customers and servers just meet and depart from the system instantaneously. The queue length in a classical queuing system is just the number of customers waiting in the system, whereas in two-sided queue, we need to take account the number of customers and the number of servers waiting in the system. So the queue lengths are the number of customers and the servers waiting in the system. Finally, the stability for classical queue is well known that if arrival rate is less than the service rate, then the queue is stable. But in two-sided queue, we'll see that the stability is not trivial. Let's look at it in more detail. Let's consider three different cases where lambda and mu are the service rates of the customers and the servers respectively. Now in the first case, if lambda is greater than mu, then there are a lot of influx of customer arrival into the system, and because of that, the customer queue will blow up. Thus the system will become transient. When lambda is less than mu, there will be a lot of server arrivals in the system, and thus the server queue will blow up. Finally, the third case, when lambda is equal to mu, the system becomes null recurrent. It is just a symmetric birth and death process, and it is well known that it is null recurrent. Thus, in all the three cases, we have seen that we are not able to achieve stability, and thus an additional lever is required to make the system stable. Now, let's look at some of the ways by which we can make the system stable. It includes adding a finite buffer to the system, so that if the queue length is more than the buffer, then we are not allowing any customers or servers into the system, thus making the system stable. Or we can vary the arrival rates of the customer and the servers with the queue length by pricing or admission control. In this work, we consider both these cases and focus on pricing as the control. Now, let's look at the model in more detail. So we have a multiple link two-sided queue with different types of servers and different types of customers, and there is a compatibility graph between them. The state of the system is the queue length of each type of customer and server. There are some arrival rates for each servers and customers denoted by mu for the servers and lambda for the customer. The queuing process is defined as follows. The state of the system is the vector of the queue lengths for each type of customer and server. The arrival process, which depends on the price, is defined as follows. So in each time step, the system operators determine the price for each type of customer and server. Based on this price, the supply and the demand curve, the arrival rates of the customers and servers are determined, and the customers and servers arrive into the system as a Poisson process with these arrival rates. The service process depends on matching, and as soon as system operators decide to match a type of customer with a type of server, they depart from the system instantaneously. Finally, the system operator receives some rewards and penalties. As soon as a customer enters the system, it pays the price posted by the system operator. The server enters the system and it receives a price posted by the system operator. And finally, the system operator receives an additional waiting penalty for each type of customer and server. So the objective of the system operator is to design a pricing policy and a matching policy such that you maximize the expected revenue in long time minus the expected Q length, where the expected Q length is the proxy for the waiting time. Let us start by analyzing the first order approximation of our model, which is the fluid model. It is defined as maximizing the expected revenue subject to just the arrival rates are balanced. Now, what do I mean by arrival rates are balanced? Consider water flowing into the system with rate expected mu1 and expected mu2 from the left hand side. Now, these blue lines are the possible routings which you can do of the water flowing into the system so that the outlet on the right side is equal to expected lambda 1 and expected lambda 2. Note that the arrival rates can depend on the queue length, but the expected arrival rate should still satisfy the fluid constraints. It is very intuitive to see that the arrival rates are balanced constraints are necessary condition for stability. Otherwise, the water will keep clogging up somewhere and the system will become non-stable. You can make this intuition rigorous by proving this following theorem. You can show that the optimal fluid revenue, which is denoted by R fluid, which is the solution of the fluid model, is an upper bound on the optimal true revenue under any pricing and matching policy such that the system is stable. Now, the natural question to ask is, can you achieve this fluid revenue? Well, not really, because in the fluid model, we ignored the queuing costs. So let's ask a different question. How about in an asymptotic regime? The asymptotic regime where we scale the arrival rates by eta and study the revenue as eta tends to infinity. This can be thought of as the arrival rates are scaled, the stochasticity of the system is going lower and lower, and it is behaving more and more like the fluid model. So the question is, how close can we get to this eta times R fluid? From our previous discussion on stability, we know that you either need to have a finite buffer or you need to vary the arrival rates with Q length to achieve stability so that the expected Q length is well defined. In addition, from fluid model, we know that it gives an optimal fluid revenue which cannot be achieved by any policy uh, under which the system is stable. Motivated by the two intuitions, we define a two-price policy by perturbing the fluid solution. The objective being maximizing revenue while ensuring stability and also keeping the pricing policy simplified. It is defined as follows. Until the Q length being up to Q max, we use the fluid solution. Thus, the arrival rates are the fluid optimal arrival rates, lambda star and mu star. Once the Q length passes this threshold Q max, we decrease the arrival rate by perturbing the fluid solution by an epsilon amount. So the arrival rates become lambda star minus epsilon and lambda mu star minus epsilon respectively. Now the question is how to pick these thresholds and second set of prices. The idea is if you pick epsilon large enough, then the revenue loss will be a lot compared to the fluid revenue loss. Whereas if you pick epsilon small enough, then the expected Q length will be really large because you are not perturbing enough to make the system stable. Thus, we need to look at this trade-off and pick epsilon appropriately. In addition to the pricing policy, we also need to define a matching policy. Thus, in this work, we consider a max rate matching policy, which is defined as follows. For example, a customer enter into the system, then we will look at the compatible servers of this customer, which is the Q1 server and the Q2 server. Now, there are 3 servers waiting in Q2 and 1 server waiting in Q1. So we'll match the customer to the queue where more servers are waiting in the system. Thus we match it to the Q2 server. Now, if the third type of customer arrive into the system and no compatible server is waiting into the system, so that customer will just wait until a compatible server arrive into the system, and then we are able to match it to that server. Just like previously, if again a type 1 customer enters, we'll match it to Q2. And for example, now a type 3 server enter into the system, we'll match it to the Q3 of the customer, because this is the only non-empty queue which is compatible to the type 3 server. Now that we have defined the pricing policy and matching policy, we will analyze the system operating under this two price policy and max rate matching policy under the asymptotic regime which is defined before. You can indeed show that the optimal threshold based two price policy and the modified max weight policy leads to eta R fluid minus eta power one third order of revenue. That means the revenue loss from the fluid revenue is eta power one third. If you divide the revenue by eta and take the limit as eta tends to infinity, you indeed converge to R fluid. The theorem also says that the rate of convergence is eta power minus 2 third. A natural question to ask is, can you do better? Can you find a policy such that the rate of convergence is better than eta power one third? So the answer is no. This theorem exactly says that. It says that the policy in the following family will have revenue loss compared to the fluid revenue at least eta power one third. A broad class of family being any matching policy and pricing policy in a broad class of policies. We make some standard assumptions on this broad class of policies, which includes bounded arrival rates, stability, etc. We don't go into the technical details of it. You can find it in the paper. So from the previous two theorems, we have seen that the optimal threshold based two price policy and modified max bid policy achieves an eta power one third revenue loss. And we also seen that a policy in a broad class of policies can only do as good as eta power one third. That means this two price policy and max weight matching policy are near optimal. Now let's look at the intuition of this eta power one third. Where is this eta power one third coming from? So if you do epsilon perturbation of the transition rates, that means you pick your arrival rates such that you do not deviate from the fluid optimal arrival rates by more than epsilon, then you can show that the expected queue length is of the order 1 by epsilon and the revenue loss is of the order eta epsilon square. Now, to match the trade-off, we will pick epsilon to be eta power minus one third, which gives us eta power one third revenue loss. Now we'll look at each of these things separately. How do we get expected value of Q of the order 1 by epsilon? We'll consider the case of single link two-sided queue because this gives us the most intuition. The work on multiple link two-sided queue is included in the paper. A single link two-sided queue is nothing but a birth and death process with arrival rates and service rates state dependent. Consider this transition rates such that these transition rates for all the queue lengths are at most epsilon away from the fluid optimal, which is lambda star and mu star. This is epsilon perturbation of arrival rates. If we have this, then we can couple this birth and death process with this MM1 queue with arrival rate mu star minus epsilon and service rate lambda star plus epsilon. The coupling is such that you are always in the lower state in this MM1 queue compared to this birth and death, compared to the absolute value of the state in the birth and death process. By Kingman's bound, we know that expected value of Q is of the order 1 by epsilon, and this indeed gives us expected value of Q is 1 by epsilon. In short, at most, epsilon perturbation of transition rates leads to 1 by epsilon order of average Q. Now, let's look at the second part of the proof, where we show that the revenue loss is of the order eta epsilon square. For a twice continuously differentiable function by Taylor series expansion, we can write this, which is a second order expansion of the revenue function R. Small r star is the optimal fluid solution, which is basically lambda star comma mu star. Here, R of R star plus epsilon is the revenue obtained by epsilon perturbation of arrival rates. R of R star is the fluid revenue. Now we can show that the first order term is zero by the fluid optimality of R star, which is basically fluid optimality of lambda star comma mu star. This indeed gives us the difference between the fluid revenue and the revenue obtained by epsilon perturbation of arrival rates is of the order eta epsilon square. This completes the proof. Let us conclude by looking at the summary of results. We first showed that the fluid model gives you a revenue R fluid, which is upper bound on the revenue obtained under any pricing and matching policy. Next, we presented a two price policy and max weight matching policy and showed that the revenue loss under this policy is of the order eta power 1/3. Finally, we showed that the maximum possible revenue under any matching policy and broad class of pricing policies is again eta power 1/3. This shows that the pricing policy and matching policy we presented is near optimal. That's it. Thank you.